I'm Anil Kumar sharing with you a very important video on the concepts of linearly dependent and independent vectors. We'll discuss linearly dependent vectors in R2, answer questions like what can they span, what do they signify. Then linearly dependent in R3, how to find such vectors, what are linearly independent vectors. We'll prove that I and j are linearly independent vectors and also see what do they span. So while working on all this, most of the questions which we'll be answering will be related to collinear vectors, coplanar vectors and spanning sets. So I think you should be familiar with these terms before we get into the discussion. So whenever we use the term span, what does that mean? Span means to write a vector as combination of other two, right? So when we say span, we could say span in R2, right? We can say span in R3. So we are going to use these two terms. R2 means 2 dimensions, R3 means 3 dimensions basically, right? So spanning really means that we should be in a position to write, let's say a vector is W. We should be in a position to write this as a combination of two vectors, right? If we could do that, then we say that vector U and V form a spanning set. Now, so it forms a spanning set. That means you can write any vector as a combination, linear combination of these two, right? So that means you can write any vector can be represented as linear combination of U and V vectors. Is it okay? So that's what it means, right? And of course, when you're trying to represent this as a linear combination, we are saying that both U, A and B are not 0, right? So both A is not equal to B, is not equal to 0, right? So we are saying both are not 0, right? So that is what it is. So this is a linear equation, and I hope that gives you a link on what we're trying to say here, right? We have introduced the terms I, j and k, for example. As you know, any vector could be written as a combination of I and j, right? So if I have a vector, let's say, let's keep it simple, R2 at present. So if I have a vector, let's say this vector, let me show it with an arrow. So whose coordinates here are 3 and let's say this is 1. Then this vector could be written as, we could write this vector u as, let's say, 3i plus j, right? I and j are your unit vectors in the direction of x and y respectively. Correct? So I hope you get this concept, what a span means, right? Spanning set means these set of vectors. You could have 2, you could have 3. Collinear vectors. The term collinear means the two vectors u and v can be said as collinear. Let's say p and q, let's use other terms. We say vector p is k times q, then they are collinear. So that means scalar multiple. Okay. So whenever we say a vector is parallel to, it is considered to be collinear, then that vector could be written as a scalar multiple of the other. Coplanar vector means, let's say we are talking about plane of this paper, then the vector shown here and this vector both are coplanar, they are in the same plane, right? So coplanar vectors are in the same plane. Correct? So these are, for example, if I write a vector, let's say 2, 3, let me write 0 here, and let's say 1, 5, 0, right? So in that case, since these two are zeros, we know they are in xy plane. So both of them are in xy plane. Or they can say z equals to 0 plane. So they are coplanar vectors. They are in the same plane, right? Spanning sets, set of vectors with which you could write linear combination for any other vector, right? So spanning set will be, we could have combinations like AU plus BV plus CW equals to 0, for example. So if you have an equation like this, which is linear combination of vectors, where A, B, C are all not equal to 0, then we say that two of them can span the third one, right? So that is a brief introduction to the terms which we are going to use in our discussion, right? We are going to redefine them also, some of them, as we move along. So now let's talk about linearly dependent and independent vectors in R2. So let me take two examples here. We are also talking about IJ. So let me take two examples. Let's say we take one set of vectors, which is let's say 2, 3, and a scalar multiple of this. If I multiply both by 3, I get 6 and 9. So let me call this vector as u and this as v. Then from here we can say vector v is 3 times u. That means it is a scalar multiple. Correct? So that means they are collinear. And that also means what? They cannot span in R2. So it means all this. So we have two vectors defined as 2, 3 and 6, 9. Vector v is a scalar multiple of vector u. I could actually represent this kind of, let me show it here itself. Let us say that vector u 2, 3 is, okay, 2, 3 is kind of like this, let's say, right? Then 6, 9 is 3 times, so it'll be, that becomes vector v, right? So we can say this is my vector u and that is my vector v, correct? So that point here, position vector here will be 6, 9. Position vector here will be 2, 3. And we are talking about xy plane. Now as you can see, they are along the same line. So if I have a vector, let's say somewhere here, I could always write that vector as a combination of these two. But if I have a vector somewhere here, I cannot span this as a combination of those since they do not have any component in that direction. You get an idea, right? So that is the reason. Okay. So that means linearly dependent vectors are kind of like this, which are scalar multiples. They cannot span in R2. And what do they signify? They signify that they are along the same line. Is that okay? So as far as linearly dependent is concerned, based on that, I can fill this up as, what can they span? They span a line. What do they signify? They signify collinear vectors. Why I and j can span R2? Because I and j are linearly independent vectors. So what I'm trying to say here is that, now let me redraw. So if I is this vector and j is this vector, I and j are unit vectors along x and y, then any vector on this plane could be written as a combination of I and j. For example, now if I consider a vector, let's say this is my vector, which is, let me say it is, let's say 4i. I could just write, let me write again. Let me write this vector as 4, 2, right? So I could write this vector, let's say p, which is 4, 2. I could write p as combination of I and j, 4i plus 2j. So for that matter, any vector on this plane could be represented as a linear combination of I and j, and therefore we say that I and j can span the whole plane R2, 2 dimensions. Perfect. I hope that idea is clear, right? We'll further get into the details of why can this not span and why can this span algebraically also. So let's move on and understand this fact. So now I'll give you reasoning about spanning sets. So I've taken up 2 examples here. First one is why 1, 2, 3, 6 does not span R2. And the second one is why 1, 2, 2, 3 can span R2. Well, the reason is this set is linearly dependent and this set is linearly independent, right? We can also say this is collinear. We can say that is scalar multiple, right? Any of those terms. Collinear and scalar multiple make it dependent. Perfect. And we will see why such vectors cannot span the whole plane. They can span a line along their direction. So let's talk about this. So we have a set of vectors which is 1, 2, and 3, 6. Now, I could also write this set as, see, 1, 2. I can take 3 common. Do you see that? 3 common. Then I again get 1, 2. Effectively, what you notice here is that I have a vector which is 1, 2 and 3 times 1, 2 along the same direction also, only, right? And therefore, if I have any other vector in this plane, let us say if I have a vector like this, I cannot write my vector W as a combination of u and v. U and v can only resolve vectors in this particular direction. Do you get an idea, right? So that's the reason. But on the other hand, let's look into the next set of vectors, which is we have a vector, let's say vector u is 1, 2 and vector v is 2, 3. Now, we want to write any other point. Let's call this point as xy now. Okay. We want to write this point xy as a combination of u and v. That means a times u plus b times v. We want to write this. Then we will say that u and v can span in R2. You get an idea, right? That's what we mean. If I do so, then I could write this as, let me rewrite here, xy equals to, when you say a times u, that means plus b times v. That means I could write this as a plus 2b, right? That becomes my x coordinate. As far as the y combination is concerned, a times u means 2a, b times v means 3b, right? 3b. That becomes the combination. Is that okay? So we can say that x is equals to a plus 2b and y is equals to 2a plus 3b, where a and b are scalar numbers, correct? So I have these two equations, 1 and 2. Let me call this as equation 1, this as equation 2. So from equation 1, if I times equation 1 by 2, what do I get? I get 2x equals to 2a plus 4b. And now if I solve for b, I can call this as equation 3. So if I do equation 3, take away equation 2, then I get 2x minus y equals to 2a cancel, equals to b. So I can write b as 2x minus y, correct? So what I have here is that b is equals to 2x minus y. Now from this equation I can write what a is. So from here a is equals to x minus 2b. So a is equals to x minus 2 times this, 2 times 2x minus y. So a is equals to x minus 4x plus 2y, or a is equals to minus 3x plus 2y. So what you notice here is that we have a set which can help us translate any point as a combination of u and v. So now any point x and y could be written with this form, au plus bv, where a is equals to minus 3x plus 2y and b is equals to 2x minus y. You get an idea, right? Now to take an example, if I say that this point for me is let us say 4, 5, let us say, right? Let us say 4, 5. That means x value is 4, y value is 5. Now if I substitute that, 4 for x and 5 for y, what do I get? I get minus 3 times 4 plus 2 times 5. And that gives me 10, take away 12, minus 2, right? And in this case for b, if I substitute 4 and 5 for x and y, I get 2 times 4 minus 5, which is 8 minus 5 is 3. So I could write that the point 4, 5 is equal to minus 2u, right? U is 1, 2, plus b, which is 3, times 2, 3. You can verify that this equation is a valid equation, right? And it does help to 4, 5, I'm sorry. So you're in a position to write any point in this xy plane with the help of these 2 points, and therefore we say that these set of points can span in R2, right? So I hope with this the concept of linearly dependent, linearly independent, and spanning set is absolutely clear. So if we have a set of vectors which are collinear, they are scalar multiples, they only span along a straight line, they cannot span any other vector in the plane. But if we have a spanning set which is not collinear, then they can span any vector in that plane, as we have shown. Perfect. Now let's move on and understand linearly dependent and independent vectors in R3, right? So now we'll talk about R3. You're familiar with ijk, right? So this is I, this is j, and this is k. The unit vectors along x, y, and z axis. Now they can span anything in R3, correct? So any vector could be written as a combination of these. For example, if I have a vector, let's say some vector here, right? So we could say that this vector is some directions in x direction, some in y, and then j, right? So you could make a box and get to this vector, correct? So you could actually represent any vector in this space with the combination of I, j, k, right? So if I write a vector, let's say 2, 3, 4, for example, let's say u equals to 2, 3, 4, it really means that we are going 2 units along x-axis, 3 along y, and 4 along top, right? So this vector could be the vector 2, 3, 4. Do you get an idea, right? So for that matter, any vector in R3 could be spanned with I, j, k. Now why they can be spanned? Because they are not coplanar. So what is important to understand here is that in R3, if we have 3 vectors which are not coplanar, then they can span in R3, correct? That is kind of very important. But in case they are in the same plane, then they cannot span. So how do we figure out whether the vectors are in the same plane or not? So in that case, if they are talking about, let's say, 3 vectors, then the combination AU plus BV plus CW equals to 0 is possible where not all A, B, and C are 0. So if that is the case, then they are dependent, right? If you get this kind of an equation, that means they are coplanar, right? So they are coplanar, right? So in coplanar vectors, they cannot span in R3, but they can span their own plane. Perfect. That's what it is. So we'll take up an example and show you how. Now, in the case of coplanar vectors, we will always see that the scalar triple product is equal to 0. Now the reason for that is that if I have, let's say, all vectors in this particular plane, let's say this is one vector, the other one is there. We are talking about vectors on this plane of paper. Let me call them u and v. Then their product, which is u cross v, will be a vector which will be projecting out of this paper. So that becomes u cross v. Now if I have a vector which is in the plane of the paper, let us say somewhere like this, in that case, this u cross v will also be perpendicular to that vector. So the dot product of w with u cross v will be 0, right? So we'll have dot product of w with u cross v will be equal to 0. And that is the condition for being in the same plane, right? So they are coplanar, okay? So that is the condition for coplanar. Now I know some of my students have not learned about dot product and cross product yet, but that will give them a brief heads up. But try to understand that cross product gives you a result which is perpendicular to 2 vectors, and dot product is 0 between 2 perpendicular vectors, right? So that will help you to understand. But anyway, if all the 3 vectors are in the same plane, they will not have a component in the other plane, so they cannot span in R3. So I hope that part is clear, right? So we'll take a box kind of a thing and then see and understand R3. So we have an example here. We'll talk in details about linearly independent vectors. So as I was saying, a set of vectors u, v, w is linearly independent if the only linear combination AU, BV, these U, V and W are vectors, plus and so on, that produces a zero vector is the one in which all these coefficients are 0. Right? If all of them are 0, then it is independent vector. Otherwise, it is dependent vector. So let's take an example to understand. So here we have the vectors. We'll call AH as vector, AB as a vector. The question for you is, set of linearly independent vectors from the following figure are, which one is linearly independent? Let's consider AB. So we have AB as this one. BC is this one. HA, so where is HA? HA is this one. You see, all of them are in same plane. Do you see that? So these are coplanar. We are talking about linearly independent. So this is not the answer. Is that okay? Because they are in the same plane, they are not linearly independent. Perfect? Is that clear? If I have a vector which is, let's say, in this direction, can I write this in terms of these three vectors? Not at all. Because we do not have any vector in that direction. Do you get an idea? So that gives you a clear idea of how coplanar vectors cannot span in R3, right? Let's look into the next example. We are now talking about AB, which is same. AC, right? So this one. And AH, right? They are again in the same plane, right? So this is also not working. Then we have AB, AF. So AB is the same thing. AF, let's see, where is AF? AF is here. Okay, so we have AF, AB is here, okay, and AG is there. Now if you consider these three vectors, so this can also not span since it does not have AH kind of a vector. It is in the plane. Let's look into this again. AB, AF. So we are only talking about this plane now. Is that okay? So this plane is actually, if I call this as X, Y, and Z, then this plane is the plane YZ plane. So this can is YZ plane. Those two could span XY plane. Do you see that? Now let's look into the last one, which is ABDC, which is DC. Okay, let's look into that one. So AB, we are now talking about AB, right? DC and AH. So now we have a vertical component. So you could say AH is along the x-axis, DC is along the y-axis. Is it okay? DC is along the y-axis, and AB is along the y-axis, right? So AB is parallel to HC, perfect. DC is parallel to the z-axis, and AH is along the x-axis. So this is the one which will span R3. Is that clear? Correct? So that is how we can see that they are not coplanar. All others were coplanar. So linearly independent vectors are those which are not coplanar, and they can span in R3. Now let's have two more questions. Question number 1. Any pair of non-zero vectors of the form xy will span R2. Always true, sometimes true, never true. It says any pair of non-zero vectors of the form xy will span R2. Well, this statement is, you can say, sometimes true, right? Because where does it fail? If I have collinear vectors, for example, 1, 2, and the multiples, 2, 4, right? 3, 6, they do not span R2, right? So sometimes, since there's one more condition here, since they could be collinear, right? So we are also looking for any pair of non-zero vectors. It should be any pair of non-zero non-collinear vectors will span, right? So that condition is missing to make it always true. The next question here is, which of the following vectors is dependent with, so dependent means we are looking for scalar multiple, right? So we have 3, minus 4, 5. This is not a scalar multiple. If I do minus, 5 should also be minus. 6, this is minus 2 times 3, minus 4 and 5, correct? So this is the right answer. This is a scalar multiple. Now here again we have a very interesting question. Solve for a, b and c in the equation twice a 3c plus 3 times c 7c equals to 5, b plus c 15. So we have to find the value of a, b and c. That's a linear equation, a linear combination. Based on this question, we have another question which says the above equation can be considered as 2u plus 3v equals to w. That means we will consider this as u, this as v, and this as w. Then you have to answer these questions, correct? Well, I'd like you to pause the video, copy the question, solve, and then look into my suggestions. Now let us solve. We are given the equation 2 times a 3c plus 3 times c 7c equals to 5 b plus c 15. So from here we can form 3 equations. So 5 is equal to 2a plus 3c, right? 5 is equals to 2a plus 3c. That becomes the first equation. Then we have b plus c is equal to 2 times 3 is 6 and 3 times 7 is 21 plus 21, which is 27. So we have b plus c as 27. And the last equation is 2c plus 3c is 15. So we can say 15 equals to 2c plus 3c, which is 5c, right? So from the last equation we can find what c is. 15 divided by 5 is equals to c. That means c is equals to 3, right? So we get the value of c as equal to 3. And substitute this here, we get the value of a also. So from here we can say 2a is equals to 5 minus 3c, which is 5 minus 3 times 3. 3 times 3 is 9, so we get minus 4. So a is equals to minus 4 divided by 2, which is minus 2. Correct? So we get a and c. Both are known to us now. So now we can write what u, v and w are. So let's do part 2 once we know this. So a and c is known. Let's find b now. b is equals to 27 minus c. 27 minus c, which is 27 minus c is 3 for us, so it is 24, correct? So b is 24 for us. So b 24, we have option c here, minus 2, 3 and 24, correct? So we get the first question. The next one here is, the above equation can be considered as 2u plus 3v plus w. Find the vectors u, v and w. So vector u is equal to a is minus 2, 3 and c is 3 for us. Now vector v as equal to c is 3 for us, so we have 3, 7, 3. And w is right there. So 5, b plus c is 27 and 15. Right. So I hope you can see this. So we got w as, I'll rewrite, w as equal to 5, 27 and 15. Now the next question is, are they coplanar? Are they coplanar? Now since you can write them as a linear combination, so the answer is yes. they are coplanar. Since you can write them as a linear combination where UV are not 0, UV both are not 0, right? So they are coplanar. Only then you can write them as a combination. Can UV and W span R3? The answer is no, they cannot span. R3. They can span R2, right? They can span R2, but they cannot span R3, right? So remember, they can span in R2, not in R3. Is it okay? So I hope that question makes things absolutely clear about linearly independent and dependent vectors in R3. So let's look into the next example. The question here is, the vectors A and B span R2. For what value of m is it true that this equation is true, right? We have to find the value of not m but k. I've used the variable k in this equation. Okay, so when we say that they can span in R2, right? So this and this both are 0. Since the vectors A and B can span in R2, that means this equation is only true if and only if both are 0. That means k square plus 2k minus 3 equals to 0. You can solve for k in this case, right? So if I solve for k, this is a quadratic equation, product of minus 3, sum of 2. So that means k plus 3 times k minus 1 equals to 0. And that gives me two values of k equals to minus 3 and k equals to plus 1. So this is from the first equation. Now let's solve the second one, which is k square plus k minus 6 equals to 0. Product of minus 6, sum of plus 1. That means 3 and 2, right? 3 is positive and 2 is negative, equals to 0. That is possible for k equals to minus 3 and k equals to plus 2. So we have these two conditions, and what is common between the two? K equals to minus 3, right? So option D is the correct option. So if k is minus 3, this is 0, this is also 0. Do you see that? Only then the equation becomes true, and therefore vectors A and B can span. Do you see that? So we say A and B are linearly independent. Is it okay? Because both are 0, right? Only then they can span. Therefore, they can span in R2. Is it okay? So that is, I hope, absolutely clear now. So with these examples, I think the concept is coming together. Another question here is, in the set minus 1, 0, 1 and a0, a square, what must a be, I mean this value a, what must a be to span in R2, right? So if they have to span in R2, what is the value of a? That's the question. So if they are spanning in R2, then they should not be scalar multiples, right? So we say not scalar multiple, so that they can span, right? So that they can span in R2, right? Now, so let's try these values. If I write 1 here, what do I get? If I write 1 here, I get 1, 0, 1. Now 1, 0, 1 is okay. It is not a scalar multiple. So 1, 0, 1 works. If I write minus 1, let me try that also. Minus 1, 0, and minus 1 square is 1, right? Now this one is minus 1, 0, 1 is the same thing. So this does not work. None of the above. So A is the right option. Do you get the idea? So A equals to 1 is correct. The next question here is, what do the set of vectors 1, 3, 2, half, 3 by 2, 1, minus 2, minus 6, minus 4 span? Okay, so let's see these vectors. We have 1, 3, 2. Okay, that's clear. The other one here is, I could take 2 common, correct? I mean, I should take half common. So if I take half common, I get 1, 3, 2. So this is same scalar multiple. In this case, I can take minus 2 common. I get 1, 3, 2. Correct? So basically, they are scalar multiples. So the question is, what do the set of vectors span? So they only span a line. So they are scalar multiples, right? They can span a line. Perfect. So that is the right option. Then the question here is, what do the set of vectors 1, 3, 0, 0, 2, 0 span? Now, let me rewrite this. It is 1, 3, 0 and 0, 2, 0. What do they span? So in this set, you will notice that the value of z is 0, right? Both. So that means they span xy plane. Correct? Or z equals to 0. So both are correct options. So option C is the correct option. Correct? So that is how you could answer this question. So I hope with this, the concept of linearly dependent independent vectors, spanning sets, collinear vectors, coplanar vectors is all clear, right? So I'd like you to go through this once again so that you can understand them in details, and then watch other videos on coplanar vectors. I hope that will help. Feel free to write your suggestions and views, and if you like and subscribe, that'll be great. Thank you and all the best.